Without doing anything, my agent from the Bronze League for CodinGame Spring Challenge has moved on to Silver League. And so now I intend to actually try to go to Gold League. But in order to do that, I think it is necessary to do some look ahead in order to search like the next best few moves. And so we will actually need to do something like Monte Carlo simulation or basically some simulation to find the next game state and so on. So because this game is, let me just load the game. This game is primarily um, to do with monster movement. Like your monster will actually move. So you actually need to do some look ahead in order to find out like where the next best move is. Okay, I think maybe to get to goal link, maybe you don't have to do that. Yeah, let me just see how my agent currently, this very naive agent that doesn't really do much as of now, is very good at defending. That's all. It's just good at defending. Let's see like how good it is against the boss. Okay, let's just take a look at how the boss plays this game, and then we'll formulate some strategies in order to win the boss. Yep. So let's see how the boss fares for this game. All right. Why is it not loading? Okay, it's loading now. So this is my agent. This is the boss. Okay, the boss seems to be going an aggressive attack strategy. You see, he's actually gaining a lot of mana right now because his troops are all like diversifying, but mine is just standing still here. So I'm losing out on a lot of potential mana that I can get. Yeah, so you see, mine is a little slow, not that great. I mean, I'm not the last in this league, but you can see that he actually has his agents more spread out in that sense. So I would like to use some form of like look ahead search in order to find out what the monsters actually where the monster position will be. So you see, if the monster goes into your zone, the monster will actually head towards your monster will actually head towards your outcome area. Oh, look at this. He's actively controlling not only the monsters, but my hero as well. He's preventing my hero from defending the. Oh, interesting. Oh, so the the Silver League AI does hero control, which can be pretty annoying. So maybe I need to do shield on my own heroes. Okay, so this is towards the end when he has mana. Let's see whose mana is actually more. So his mana, he actually outfarmed me in mana. He has 330 mana for this boss. So I think a key idea to winning this game is actually to farm a lot of mana at the start of the game, and then like towards the end, maybe the last 50 or 100 time steps, uh, you kind of need to shield your hero because you see people actually do cast spells on your hero. So you need to have enough mana to cast shield continuously on the last few turns on all your heroes, and also you will need to have enough mana to actually push the opponent's base because I think a pure defensive strategy towards the end when the monsters have the 22 or 23 health is not going to cut it because like if you just do control, do shield, do win, I think you can easily overwhelm the enemy's defense. You look at the number of monsters there are over here compared to the beginning. The beginning the monster is 11 health, but towards the end the monsters are 21 health. Okay, so anyway, that's not the point for today's stream. The point for today's stream is to do a look ahead search, and yeah, let's try to code the look ahead search. So given the monster's position, I want to find out where the next position will be for the monster. So let's see what the okay, let's see how we do this. So the stream, I think I'll break it out into two parts because I still want to code the Monte Carlo simulation in the end to maximize my wild mana farm. But in order to maximize the wild mana farm using Monte Carlo, I first need to find out where the next few positions of the monster will be. So let's find out where it will be. So okay, where's my input for the monster? Okay, I'm trying to find out because every time you take in an input, you actually have a few parameters for the entity. I'm trying to find out where it is. There we go. Next five positions will be applied for monsters. Health, okay, health we can skip that for now. Vx, Vy, which is monster current speed position, and near base. So I think there's a distance each monster can move. I'm not too sure where is the distance here because we only have this monster's current speed vector. Mm, I don't know. Is there a way to find out the distance the monster can move? Because we kind of need to simulate that. Okay, let's just see this. I think one way to do it will be to just take the speed vector and then just take the magnitude in order to find out the how much the monster can move. So let's define a code. Okay, so let's define predict next pause. I'll just make it a little lengthy. So the predict next pause function, this takes in the current monster position and outputs the future one. Okay, so that is quite simple. Okay, but because we need to also factor in, okay, you also need to factor in the proximity to base. Okay, so I will not do any prediction for like the spells because I think that's a little too hard to predict. So in order to do the next position, okay, we have the monster's current position. We have the monster's velocity, which is the speed vector. Okay, and then there's also a need to check whether the monster is near the base. So what we need to do is, okay, we have our base pos. We also should have our op base pos equals to op base x. So let's have the op base pos and base pos. So basically what we need to do is we need to check. Okay. Okay, so the next position, okay, so it's not really just predict next pos. It's predict next pos and velocity. Maybe we just put predict next pos and vel. Future and outputs the future position as well as velocity. So the first part is very simple. Update monster's current movement vector. So maybe you have a new pos equals to new pos x, new pos y equals to current pos. Okay, new pos x plus equals to velocity 0. New pos y plus equals to velocity 1. We basically update the movement vector. Okay, if the monster is outside of the, so actually we need to see whether or not the monster is at this part here because there's this sort of line here, right, that we need to find out. um Basically there's two over, how wide is this, how wide is this non-shielded area? Do they explain where the shield area is for 3 points of damage? Let's push with a win, 5,000 units. Okay, check whether the new position is towards a base. So when targeting a base, monster move directly towards that base. Okay, getting pushed with wind within 300 units as long as it will disappear and do the base. Okay, so it's within 300 units of a base. I guess this is 300. Okay, so I do have like a very weird exposition here because the exposition shouldn't be negative. Not sure why here is negative. So unless the 0 0 position is, I thought the top left was 0 0. Yeah, so I think there's some issue with the top left is 0 0. So maybe we start from the beginning. Yeah, something wrong with the visualization here because 0 0 is supposed to be here top left, right? Okay, so I just gonna assume that the fence is at 300 meters from the base because it doesn't matter if it's outside. I mean, it doesn't matter if okay, basically if the monster is within 300 meters to your base, it will disappear anyway, so it doesn't matter. Okay, let's okay. So the first step after we get the position, we will need to update the position. So we will update the position based on the fence over here, because only when within this fence, then it will stay within the map. Yeah, I think they mentioned here that if it touches the fence, then it will. If a monster is pushed outside the radius, it will stop targeting. Where's the fence part? There should be a fence that the monster, because if the monster hits the fence here, it will stay at the current position. So let's see whether there's a mention of the word fence. Nope, there's no mention of the word fence. Let's see. When targeting a base, where's the fence? Where is the fence in this whole detail here? A monster can be pushed outside the map unless it is a base radius in which it will be moved no further than the border. Okay, so it means that if monster within the base, then the monster will not get out of the map. Okay, so if okay, so I need to define a distance. Okay, so maybe we put a distance to base here. Base equals to distance, new pos. Okay, so maybe we just put new pos equals to new pos x, new pos y. Okay, equals to distance new pos my base. Is it that base pos? I put base pos. Okay, distance to op base, op base pos. Okay, so we if monster within the base, if distance to base, okay, it's smaller than 5,000 squared. Okay, 5,000 then or distance to opponent base. Actually, I can just do like this. If min is if this is smaller than that, okay, then we will need to adjust our parameters. So new pos x, new pos x will be equals to the min of. Okay, so it really depends on whether the base is to the top or the bottom, but either way it won't get out the map, so it means that it will be minimum of x is from x position is from 1760 to 17630. So click value in Python, I wonder if there's a clip value. If not, yeah, there's a numpy clip. You can limit your values here, or you can do like max and min over here. Yeah, max min, or we can use numpy clip. Yeah, so I think I'll use max min because I didn't import numpy for this simulation here, so I just use max and min. So if let's say the monster is within the base, then we will clip the monster position from 0 to new pos x, and then the maximum position will be 17630, and new pos y equals to max min, the same thing, 0 new pos y, and then what's the other one, 9,000. So it will never get out the map, okay, if it's within the base, because there's a shoe here. Okay, so then we need to check whether the new position is towards the base. So actually um this is the same thing. So if let's say this is towards the base, then what we need to do here is to update the movement vector towards the base. So what we need to do is, okay, maybe because in this case this is generic. Okay, so uh, okay, let's see how to do this. Okay, because I do not want the monsters to move anymore. Okay, so maybe what I will do is I will have another vector here called next velocity vector. Maybe we put 0, 0. So if the monster is out of map, okay, then return velocity of 0. Okay, it means that the monster is like sort of destroyed. Okay, so what we'll do is like this. If new pos x. Okay, so actually something to do with this. Okay, so or new pos y smaller than 0 or new pos y greater than 9,000. Okay, return. Okay, new pos new val. Quite new val. Okay, so this is the, because monsters we only need to know the velocity for the next position as well as the new next position and next velocity for the monster. So that means this will not move anymore. Yeah, because the monsters when they get out of the map, we can just treat them as non-existent. Yeah, I mean we can do a code to delete away those monsters from the simulation, but that can be done later. So this is if the monster is out of the map, then we return a velocity of 0. Okay. Next up, we need to check whether the new position is towards a base, and then like update the monster movement vector towards a base. So first, we just check whether it's towards like your own base. If it's towards your own base, okay. So 5,000, right? If I'm not wrong, it's 5,000 units within the base. So if it's towards your own base, okay. So what we need to do is we need to find out the magnitude of the velocity vector. So what we can do is the magnitude is equals to the square root of the velocity 1 and velocity 2. Velocity first term squared plus velocity second term squared. Okay, and then you take the whole thing to the power 0.5. So this is the magnitude for, so this is like distance to move. Okay, so if the velocity towards the base is sorry, the distance towards the base is smaller than like the radius, then we update this. Okay, new val equals to get next val. Okay, so we need sort of like the angle towards the base, because like if the position is here and the base is here, we need to sort of get the relative uh we need to get a vector towards that base position. Okay, so we have a distance here. We need the angle towards that base itself. So in order to do that, let's see how do we get that. Okay, so if let's say that the monster is here, he will travel straight line towards the base. So we need to find out the magnitude. Just draw. Can I draw here? We need to find out. Okay, where's my line? Yeah. So something like this. I'm using like the draw function on the coding games Twitch. Sorry, the Twitch. It doesn't look very good. Yeah. Maybe I should use like another tool. Okay, let's clear this. Okay, let's clear that. Uh, clear clear all drawings. Okay, so let me just do, yeah. So maybe what we can do is like this. Yeah. Okay, you have a vector going towards one position. Okay, maybe this diagram is good. So you have a vector going from here to here. You need to calculate the angle here. Okay, so the magnitude we have calculated already is x squared plus y squared, the velocity, and then you get this magnitude. So what we need to do now is we need to find this angle, okay, that gives us the angle towards that particular vector. So in this case, there's only two possible situations. One situation is it goes to the top left, and the other situation it goes towards the bottom right, because the bases are only top left and bottom right. So based on this theta here, we can get like magnitude cosine theta or magnitude sine theta. So okay, this is for the case of the first quadrant. Okay, I mean, of course, when we do different quadrants, we get different angles. Okay, but let's say first up, I think it is safe to say that we need to find out this angle here. Okay, and this angle theta that determines the direction of where we go next for the monster, that angle theta. I think this angle theta can be calculated already, okay, because we have the x and y values of the movement vector even here. So there's a movement vector here. The movement vector is given as velocity 0 and velocity 1. So I think it is possible to just take a inverse tangent, arctangent, and calculate the angle. So let's see how to do arctangent in Python. So arctang in Python. So I think it's as simple as a10. So math.a10. We need to import math.a10, and then we just do the. So we probably will need to do it uh, for, okay, so based on this angle theta, because we already have the movement vector x and y, we can get this angle. Okay, so actually this is not the movement vector that we are getting. Okay, this theta here is the distance towards the base. Okay, so if it's towards the towards your base here, okay, so we need to get like next angle equals to, okay, so let's import math.a10. So we need to take the, so like over here, where's my diagram, this part is like your base. So in order to get the length, okay, because let's say the base is here, your base is always top left, right? Okay, but it's not that safe to assume, because your base can be top left, but you can be a flip position. Are you always 0 0 in this game? Will you always be a 0 0 base for this game? Because if you always be a 0 0 base, it's quite easy to do it. I'm not sure whether your base will always be at 0 0. Will your base always be at the top left? I mean, it appears so. I mean, yeah, but we cannot assume so, because like, sometimes you might appear here if you are the second player. Then your base will be at the bottom right. So in this case, if let's say your distance to base is less over here, we need to find out like what's the distance between like here, this x vector. Actually, what we can do is very simple. We can just do a magnitude. So we just take the absolute that. Yeah. So what we can do is, okay. So the a tangent. I think when you do arctan, your arctan will give you like the positive or negative values of this. You can just do an absolute value outside of the arctangent, and it will still give you the same angle, I believe. Yeah. So maybe you can put the absolute value outside. I mean, we can do some testing, see whether it works. So we do the absolute value outside here. then we need to do the arctangent of like the first vector divided by second vector. The first vector will probably be base pos 0, okay, minus, okay, the current new position. Okay, so actually we can use base x and base y because we also have that base x. Okay, is it x over y or y over x? Y over x, my bad. Y over x. Okay, so this the we can also probably do the same thing for the other one, but we'll do it later. So we do it for your own base first. If distance to base, you find out the angle to your base. Okay, and this angle will be this angle here. Okay, it's going to be the angle with respect to the x-axis. Okay, so after we get this angle here, we can then proceed to move, okay, towards the velocity that goes next can be based on the angle also. So if it's towards your own base, okay, and the base uh x and base y is like smaller than the monster itself, that means it's like the top left. If the base x and base y is greater than the monster itself, then it's at the bottom right. So I think one way to do it is to just see whether or not uh you to just see whether the, okay, so maybe this distance to base here can be the same thing. Actually I can use the same thing because I think the key thing to find out is whether or not the, oh, actually no, we use a different one because we have base pos y and base pos x. Yeah, what I need to do is I need to find out whether or not I should subtract my x and y or increase my x and y accordingly. But anyway, we can just do the new velocity 0 equals to, okay, so in this case I use a tuple. This is, I shouldn't use it. I should use an array, okay, because if you use a tuple in Python, tuple is immutable, so you cannot change the contents within the tuple. So if you use an array, you can change the contents here. So we can set the new velocity here, okay, to basically yeah, we are finding out this magnitude now, x and y. Okay, and what's this base magnitude here? This base magnitude here is basically the distance to move right here. Okay, maybe I can just put velocity magnitude, right? Make it clear. Velocity magnitude is this. So x component is magnitude, cosine theta, and sine theta. Okay, in this case, my theta here, okay, actually I don't have to do a absolute value of the angle here, right? If my angle here, like over here, ya over xa, right? If let's say this ya, I take this minus this, and then sorry, ya is this minus this, xa is this minus this. If it's positive, it's naturally here. If let's say both are negative, then if let's say one is negative, if the base is here, both x positions, x will be negative, y will be positive, and again in this case cannot because the CodinGame one is 0 0 at the top. I'm just thinking whether I can just use the absolute, without absolute the angle, can I use it? I don't think I can, okay, because it's not really a Cartesian coordinate system in the CodinGame side. Okay, we probably just need to take the x and y components in terms of the, the absolute values, and then later we update whether is it a positive or negative update based on the position again later. So let's do the x and y component. Is magnitude cosine theta, and given that this angle theta is always going to be positive, magnitude cosine theta will always be positive. Same thing for magnitude sine theta, because given that this theta is always in the first quadrant of this whatever this is, okay, we always make theta in the first quadrant. Sine and cosine will always be positive in the first quadrant of your Cartesian coordinate system. So let's see sine in Python. Sine and cosine. So it's probably math.sine. And the syntax is math.sine of the value in radians, which is great because arctangent gives you the arctangent between in radians as well. So if we do sine in radians, okay, we basically don't need to do anything. So let's do new velocity 0, okay, equals to, okay, velocity magnitude, okay, times, okay, math.sine next angle. Okay, same thing for new velocity 1 equals to velocity magnitude times math dot cosine. Okay, so I need to check again whether this, so this is the magnitude in the x direction. So let's see whether this works. Magnitude in the x direction equals to magnitude cosine theta, because cos is adjacent over hypotenuse. Okay, so it's wrong. It's math dot cos and math dot sine. Okay, so okay, then this is for one case. Okay, uh, we also need to check now. Okay, check whether monster is, check whether base is top left of monster. So if the base pos x or base pos y is like smaller than the new pos y, that means it's top left. And base pos x smaller equals to new pos x. Okay, then this is top left. Okay, this is, if the base is at top left, okay, my new velocity, okay, 0. Okay, because both are positive values, okay, we actually need to make them negative. Okay, new velocity. Do I put new val? Yeah, new val. Yeah, so only this case, if it's at the top left, we do a negative velocity. So check whether new position is, so actually we do have a huge chunk of repeat code here. So check whether new position is towards own base. Okay. So this one we need to check whether the position is towards opponent base. So this one is distance to op base. Okay, if this next angle equals to this, and base pos, this will be op base pos. Okay, how do I put it? Op base x. I just put op base x. So actually this is not base pos y, this is actually base x and base y. Why are this in base pos is not defined? Okay. Okay, so it appears that I will need to put this definition of the functions. Like I need to define all these base positions before these functions in order for this to work. So let's just put this here like that. Yeah, so that I get all this at the beginning. So all this would work now. Okay, distance. I cannot define distance yet because distance is referred to in this code. Distance need to be given earlier. So like that. So base x, base y, op base x, op base y. Okay, so this distance of base, the same thing, exact same thing here. Okay. Why is this still in curly? Oh, oh, I see. Okay, why is next angle still in this? Because I didn't do a tag. Same thing for here. Okay, if the base is top left, actually in this case, this should be, yeah, actually this is still the same. If the base is smaller, then we will do the negative vector. Same thing here. Okay, if base is this, okay, then at the end of this, what we need to do is we just need to return new pos, new val. Okay, so what I want to do is, oops, what I want to do is I want to just see whether or not this short and simple movement prediction code. Okay, so we only need to predict monsters because monsters are certain. Monsters are controlled by the AI of the game simulation engine. Okay, so if we just assume that the monsters move in a fixed path without any intervention by the heroes, we should get perfect prediction of where they will be. Okay, there's actually a small catch over here. I think there's some technical things that I saw like a few days back. Technical details. Um, something round up or round down. Let's see. Where is it? I remember there's something about rounding up and rounding down in this game. So where is it? Now I cannot find it. Now when I want to find it, I can't find it. So where's my round up and round down code? Um, okay, so I'm very sure there's some technical details that we saw earlier. Okay, I think they removed it. Okay, there's no round up and round down anymore. There should be a round up, round down if I remember correctly. So where is it? Okay, doesn't matter. Okay, doesn't matter. I think a distance of one wouldn't affect the code that much. Okay, it wouldn't affect that much. So okay, one thing I want to do is I actually want to abstract out this code. Okay, to be something like move towards. Okay, so what we can do is like this. Okay, we can put like new val equals to move towards. Okay, and we can put like base pos, base base pos, and then this will be the new pos. So this should be like that also. Yeah. So instead of doing like new pos x, new pos y like this, I can refer them as 0 and 1. Or maybe I just do away with this new pos because like it seems that this redundant. So maybe we can just do like new pos x and new pos y over here every time we need. Oops, I deleted something. So over here, because I keep referring to new pos x, new pos y, so I'll just like just do it like that. Yeah. So if we have like a pair structure in, I mean, I guess you can use a dictionary structure, but I think just referring to like that might actually save some time. Okay, not that Python is very efficient. Python is actually very inefficient. I might need to recode the entire Monte Carlo code that I want to do in C++. Okay, that's if I have time. But if not, I can just run fewer simulations. I'm pretty sure that just using some heuristics can get into Go. So yeah, for those who want to try Legend, I think you have to use C++ because uh, you definitely need to simulate more game states ahead. Okay, this coding game problems are usually just state search problems. See who search states better. The more states you search, the better your certainty of taking the action because you consider like more future states, and also your heuristics if you are trying to do a approximate state search. Rather than searching through the states in the future, you can also do an approximation of the states using some heuristics. So that's what we will do, okay, for Python. Okay, so now what I want to do is I just want to shift all this stuff here into a function called move towards, and this will return like the new velocity here. So let's do that. Let's do that. define move towards goal pos, original pos, and then maybe magnitude. Okay, so this returns uh, the velocity vector heading from original pos to goal pos with a certain magnitude. Okay, so we have this next angle equals to, so I want to make it generic because later on I want to do that for my heroes as well. So we can use the move towards for heroes as well. Absolute math dot a tangent, this one. Okay, so instead of base y, we can put goal pos now. Goal pos 1 minus original pos 1. This one will be goal pos 2. Sorry, goal pos 0 minus the original pos 0. And then we have a new velocity here. Okay, so we can just call it vel x and vel y now. And then so it will be the magnitude. Okay, then probably we want to make this an integer because the magnitudes are only integers. So what we'll do is, no wonder they say round up or round down, because if we use like stuff like this, this will do the rounding. This will actually round down. So yeah, I think it's pretty much in line with what CodinGame does. Okay, so we return the velocity vector like that with a move towards. So we have a move towards new base pos, original pos plus vector. And then after that, we check whether the base is, so this one we return like this. Okay, check whether the magnitude is, if it is, then so over here the new pos we have to return back as return new pos x, new pos y, new velocity. Okay, so here we can replace also, and replace with this. Okay, did I do it right? Okay, so I don't know whether I did it right. Let's just run the code, okay, without doing anything to just see whether there's any compile errors. I'll be amazed if there's no compile error because like I didn't even test the code yet. So it should run for the game. Oh, there's no compile error. Wow. Okay. Okay. So looks like is are my heroes moving? Yeah, okay, they're moving. Okay, so now what I want to do is I want to do a check of the next position for the monsters by running through this predict next position velocity function, and we see whether or not we can predict. Okay, so okay, so here predict, what's the function called? Predict next position velocity. Okay, what's my function input? My function input is current position and the velocity. So the current position will be each position, and the current velocity will be each. I think I save it under velocity trajectory. So we just want to see whether we get this next velocity right. Okay. Okay. So what we want to do is we can print this. Okay. Monster at this position. So the position that we want to put is each position. Okay. And then future position. So actually we have next pause and next velocity, right? I remember it's returning both. If we see the function, yes, new pause and new velocity. Future position will be each velocity. Sorry, no, this one will be next pause, and then the future future velocity will be okay. So let's see whether okay. Then we can just like print this to system.standard error. Okay, so the monster future pause over here. This is what we are currently printing out. Okay, these are the future positions of our monsters. Okay, which we actually don't need to do anymore. Okay, so this enables you to predict one step ahead. But with this, we can predict not just the future position, we can also predict the trajectory. And actually, what we can do is we can then predict the next x positions. Like so, instead of predict next position velocity, okay, I guess actually the velocity is not that important for the Monte Carlo simulation. What we can do is we can just predict the next x number of positions and see whether it works. Okay, but for now, let's just see whether this does work. So what we can do is we can have a monster future velocity because we already have the pause over here. So I mean the position should be the same as what we predict earlier, just that some of these positions might be outside of the grid. Okay, monster future velocity will be like this. Append the next velocity. So we can append this for all the monsters. Okay, I don't think we need to append the velocity in the future also. Okay, let's see. The thing was not closed. Why? Yeah, I miss out. Yeah, I miss out something for this print function. Bracket was not closed. Okay, this is a f print, so this should be okay. Could it be that it doesn't allow slicing of the thing into two parts? I have no idea why why there's an error here. Let's see. Let's just play and see whether there's any error. Unmatched bracket 129. unknown variable each. Isn't it here? Yeah, I'm just gonna put these two lines together and see whether there's any issue with the. It's weird. That's weird. Okay, let's just put a new variable called current pos. Not sure why they don't allow this, but let's try this. See whether it works. Okay, so it seems that they don't allow like the each to be in the system for some reason. Okay, now let's see the updated future position of my monsters. Future position 3451, future velocity 00. So it should be 34515619. Let's see. Yeah. Okay. Future velocity 0, which is weird because it's not supposed to give you 0. Okay, let's just see a while more, see whether there's any more. 32226577. This one. Future position 33996935. Somehow this is like from the previous state. 3451. This one is 3327. Okay, let's just see from the start again. Okay, so we have a monster at 3575 5999, but somehow the future position they put as like, somehow this doesn't look like the future position for each in important monsters. See, I have my future pause here. Yeah, this is weird. Okay, this is weird because I'm having someone have a monster at 3575 5999, of which it's not really shown here. 357959, 34515619. Yes, that's correct, but the future velocity is wrong. Okay, so it means that there's this issue with the next velocity function here. Okay, but the current pause over here also does seem a little out. Okay, so maybe let's just print maybe like future pause. Okay, let's see whether the future pause is the current pause or not, because the future pause is supposed to be the future prediction. Okay, which we already know works because it kind of worked for the initial part. Let's see. Okay, so where am I? Okay, monster at 4118 3050. So actually the future position matches with this calculated future position. Is that maybe we okay, the monster is at 34159 right now. Okay, good. So here we have nothing. Here we have two monsters. One is at 24354745. This is the future position. So it means that actually the output screen was displayed slightly earlier. So okay, no biggie here. Our prediction is correct actually. That's great actually. We can see directly the future position and see whether it matches. Okay, so we don't need this anymore. Now we just want to find out why our velocity that is predicted is at 0, 0. Okay, because the velocity is supposed to take into account this velocity magnitude as well. So let's see why. Okay, so I think it's because if it's not towards the base, we return 0, 0, but we actually supposed to return this thing with with, with the current velocity like that. Yeah. So the current velocity, maybe what I will do is I'll do like that because I want to make it uh, editable. Yeah, let's just do like this. Oops. Yeah, let's just do like this so that if we ever do not have it near the base, the velocity here would be a non-zero velocity. It will just take into account the initial velocity here. Yeah. In fact, actually, what we can do is we can just like um, because we don't have the velocity until later on, right? So and actually we don't really need this new val at all. The new val can come from here, so we can actually just return velocity here and then omit this part here. I guess everything is referring to the original velocity. We don't need that thing there. Okay, so let's play and just find out whether or not the velocity matches, especially for those creatures that enter the base. Okay, something went wrong here. Let's take a look. Local variable new val reference before assignment. Okay, this one. Okay, here I'll return 0, 0. Okay, but then I will need a new velocity here. Maybe you can just do it here. Okay, yeah. Okay, let's see whether the prediction is accurate because now what we're doing is we're doing some monster prediction. So we should have two monsters. Let me expand this thing here. Okay, so it's actually quite lengthy in terms of yeah. Okay, so I have this monster here at three 34753859. Okay, but the future position should be actually 3208. Okay, but it predicts the future position as this 176309000. Okay, so obviously somewhere the future position prediction here has gone wrong. Okay, but let's see the future velocity minus 355 minus 181, which kind of matches, right? Minus 355 minus 181. Okay, so our future position is wrong. Let's see why that is the case. Okay, because I put new pos x, new pos y as the position, and new pos x, new pos y is max in this one. So this in this case, this should be min max, I guess. Okay, that should solve one part of the problem. Let's try to play again and see how. So it means that I think the magnitude is soft. Sorry, the future position should be soft when it's in the base. Now the issue is the angle. So let's take a look at whether or not we can get this right. Okay, so let's see. This is 4063, 5543. Future position 3766, 5277, which is correct. So all the monsters that are outside of the base is correct. Do you just see that? The monster just went out. Yeah, so okay, apparently this is not part of the base. This can still float out. Okay, I guess it's not within 5,000 yards yet. Of 5,000, I think 5,000 is around here. So may have slipped by. Yeah. Okay, so we have this monster here. It should be at 3528, 4768. Future position 3429, 4381. That's correct. Okay, now it has entered our base. Yeah, so this should be at 3231, 3607, which is still correct. Okay, now it has entered even more. So this should be at 2965, 3310. Okay, still okay. Okay, now it has been mind controlled. So that means the. Oh, wait, no, mind control is mind. Yeah. Okay, so we have this monster here. Let's see. Okay, so this monster is within the base. It should head towards the base. So this is at 4764, 1519. Future position 4383, 1398. That's okay. So it hasn't really reached the base yet. This one will be at 4002, 1277, which is correct. Now here it will be 3621, 1156. Correct. Some more 3190. Okay, this is wrong already. So here it is currently at 3240, 1035. So this monster was at 3621 before that. It moved towards the base. Okay, and it actually should move towards 3240, 1035. Oh, actually that's correct. It's still correct. 3240, 1035. Next one, it's at 2859914. Oh, great. Okay, it's moving towards the base, which is exactly what it should. This one it's supposed to be 23893074. So let's take a look. 23893073. Okay, it's correct. It's still correct. This one 2478793, 21442758. Yeah, I think in general it seems to be working. Like here, this 27162338, I get 27162338. Yeah, nice. The other one is at 2982. This one, I think the future position is at 26754679. Okay, so actually I kind of want to do a prediction at the opponent's base also. Okay, so I kind of need a hero here in order to do that prediction. So okay, let's just look at this monster again. I want to see a monster that changes direction halfway into to the base. So let's try to find a monster that maybe this monster here. Here is 623, 4983. Okay, correct. This one 361, 4682. Yes. Okay, now it changed position. So this okay is supposed to go to 331. So actually this is not the base. Okay, the graphic overlay got some issue. The base radius actually here 5,000. So this is 3314284. Yes. Okay, so everyone, the predict next position velocity is kind of working for my own base. I haven't checked for the opponent's base, but this is a good start. Okay, it means that you can actually predict the future X positions for the monsters, and then the heroes can then later on I will implement a form of Monte Carlo in order for the hero to optimize the amount of mana farmed based on all the future position predictions of the monsters. Okay, this is very important because I think farming wild mana is the key to winning this game. Okay, only when you have farmed enough wild mana can you do very aggressive attacks and spells on your opponents. So yeah, let's see where this leads us to. Okay, but I'm quite happy that this has already reached the correct position. Like over here, 331, 361, 4682. Next one. Okay, let's do it. This 9992019. Very good. 3314284, and the other one is at 293253. Okay, looks like our angles are working. Okay, let's look at another one that changes position halfway, like this one. 4712 763. This one goes to here. This one is from here, and then after that it changes position to 4318700, and indeed it's registered here. So I'm quite confident that uh, it is able to work. Right now I just want to see whether there's an instance of a monster getting out of the map. Okay, but going back in because of the algorithm. So let's try to play this scenario again and see whether there's an that moves beyond the map itself, and then we predict its position backwards because of the fencing. Okay, let's see whether we can do this future prediction thing correctly. Okay, let's see. So using this predict next position velocity, I actually factor in if the monster is out of the map. Sorry, not this. If the monster is within the base, okay, the monster will not move out of the map. So this is something that needs to be implemented in order to simulate the future positions. Okay, let's look for a case where the monster is out of the map, but because of it being in the base, it went back to the map. Okay, maybe this one here. Okay, so unfortunately, I'm not able to simulate that case because uh, I think in general the movement vector for these monsters are quite low. You need it to be like really at the edge here in order to get it to reach that situation. Yeah. So here is like 262951631, and we indeed get this prediction, which is great. We try another case where the monster turns halfway again and see whether it predicts correctly. Okay, like this monster here, 1110 1110 5089. Okay, next 86356 4 8634775, correct. Next one 7924382. Okay, sorry, 7924382. 7924382. Okay, so I'm quite satisfied with the next position prediction. Just a recap, like especially for those who just came in, is just using this method where we take the existing magnitude, okay, and then we take the distance from the base. So like A here is the base position or the opponent's base, and this is the current position for the monster, and then we just simply take the arctangent, or in Python you use the A10 method, okay, and you take the arctangent of the y over the x in order to get this angle. For me, I make this angle an absolute value so that I always get within quadrant 1. Okay, then I can get the x and y component of my new velocity by taking this magnitude, okay, times cosine theta, and magnitude times sine theta. And this magnitude is actually obtained from the original trajectory vector that was given for each monster. So we have the x component and the y component here. Then we just check whether the base is it to the top left or to the bottom right. If the base is to the top left, the x and y velocity updates will be negative, like this. If the base is to the top left, the velocity updates will be negative. Okay, so these are just how I did this next movement position update. Okay, next up, what we need to do is we need to come up with the future, maybe I think 5 positions of my monsters, and then I will perform a Monte Carlo sweep of each hero going within its radius of 800. I can sweep within a certain angles. Okay, maybe I think I'll aim about 10,000 simulations maybe, and then it'll find the simulation that actually gives rise to the most wild mana farm. Okay, so yeah, stay tuned for that. I didn't really improve my rank in this league as of now because I'm still trying to get the simulation mechanism going. But I'm pretty certain that once everything is done, should be able to get the goal league. Okay, and yep, that's all for now, and see ya. Bye bye.